Hello, welcome back. Today we're going to be taking a look at the natural basin integration. Before we begin, let's evaluate the following derivative. Just a little bit of review of our second FTC here. And you might recall for the second fundamental theorem, we're taking the derivative of an integral. So for the first one, we're taking the derivative as we go from 3 to x cubed of the natural log of t squared. So when we take that derivative, well, since I'm taking the derivative of the integral, we should get this natural log of t squared back. But using the fundamental theorem, our rule just says we're just going to replace each t with x cubed. So this, of course, becomes the natural log of x cubed squared. And don't forget the chain rule. We're going to multiply by here as 1 to the t, and that's the derivative of x cubed. The first one will simplify to the natural log of x to the 6 times the derivative of x cubed, 3x squared. And there we go. Again, we don't have to worry about the 3 because that's just a constant. When we take the derivative of 3, it just becomes 0. Now that's different for part B right here. For part B, when we replace the t with the sign of x, we also have to replace it with x as well. So this is going to be like our FTC, like the f of sine of x minus f of x. And then we take their, of course, their derivatives. So what we're going to get is the square root of sine of x minus 3 times the derivative of sine of x, that's our chain rule, minus the square root of x minus 3, can now replace it with my x, times the derivative of x. So here we get the square root of sine of x minus 3 times cosine of x minus the square root of x minus 3 times just 1. And there's our derivative right there. So today we're going to be taking a look at the natural exponent, base e. You might recall this is one of Euler's numbers, and e is approximately 2.71. Earlier this year, last semester, we talked about the derivative of e. The derivative of e is just itself, e to the u, times this u prime. This u prime, of course, is just our chain rule. So some examples, if we're taking let me read, that's a terrible looking R right there. There we go, chain rule. So if we look at an example of the following using the following derivatives, don't forget there's always a chain rule on these. So for number 1, if we were to take the derivative y prime, the derivative of e to the 4x squared is e to the 4x squared times the derivative of the 4x squared, which is just 8x. We don't worry about the 3 because that's a constant. It's just 0, and there's our derivative. For a question like number 2 here, we're going to use a bigger chain rule. The derivative of the outside, the derivative of sine, it's cosine of e to the 3x, multiplied by the derivative of the inside, which is e to the 3x, times the derivative of 3x itself, like a triple chain here, times 3. And there's our derivative. That is about as weird as they come. When we want to take the antiderivative of e to the x, we just do the exact opposite. So if the derivative of e to the x is e to the x, then our question would be, well, what's the antiderivative of e to the x? Well, remember, this is just the inverse of the derivative itself. So if our derivative again is e to the x, the antiderivative of e to the x is also e to the x. But because it's an antiderivative, we need that plus c. And there's our rule for today. Very simple rule. So that's our rule here. So note, we're going to be using u substitution. That's why we got this u here. And don't forget your constant of integration. So let's take a look at an example. For number 1 here, we want e to the 3x plus 1. This is a u substitution. Notice u is always going to be the exponent in these. So we're going to let u equal 3x plus 1. The derivative is going to be 3 dx, giving us dx is just du over 3. And I'm just going to rewrite my integral. This becomes 1/3 e to the u du. So our rule, we get 1/3 e to the u, well, e to the u plus c1, and then I just got to replace my u here. So we get 1/3 e Our u is 3x plus 1, plus don't forget your constant of integration right there. Very easy to do these. Let's take look at a couple more of these and we'll take a break. So for number 2 here, I got the integral of 5x e to the negative x squared. Well, again, if I look at my exponent, that negative x squared, that's going to be my u. So we're going to let u equal this negative x squared. Our du is negative 2x dx, giving us dx is du over negative 2x. Another way I know that my x squared is going to be my u is that the derivative has an x in it. And I know they're going to cancel out, which we're going to see in a second. If we rewrite this, we get 5x e to the u du over negative 2x. Ah, there they are. Those x's cancel. And if I rewrite out my constants, I got this negative 5 over 2 e to the u du. Make your work look nice and neat and organized. When you write your answer, we get negative 5 halves. The antiderivative e to the u is just e to the u plus c1. And the last thing we're going to do is replace u. We get e to the negative x squared because that's my u. Whoops, not there, not there. Plus our constant of integration. And there's our answer. So pause it and try number 3. Our u here will be this x cubed. And I'm going to go ahead and do it, and so you can pause it and come back to the video. If we let u equal this x cubed over 2, the derivative would be 3x squared over 2 dx. That's a weird looking x right there. So we would get dx equals, now when I multiply, we're going to get this du, but I'm going to invert and multiply everything here. So this becomes 2 over 3x squared, and that's really what we want. Substituting in, we still have the x squared. This becomes u, e to the u, and we can get this 2 over 3x squared du. Now again, the x squareds have to cancel. If they didn't cancel, we did it wrong. My constant is this 2/3, so I can just bring that out to the front. It does make it a little bit easier. And we get e to the u du. So integrating, we get 2/3 e to the u plus c1, and just replace u. 2/3 e, our u was this x cubed over 2 plus our constant of integration. And there's our answer. All right, I'm going to go and stop this video here, but go into the second part and you can take a look at some more examples. I'll see you then. Bye-bye.